Today I am going to discuss about the introduction to Schrodinger equation. Basically, what is Schrodinger equation and what is the impact we are having about Schrodinger equation? For example, if you are run out of the petrol in your car, what you will do? You will just come out of the car and you try to push the car. But as we know from the Newton's law, what he proposes is that the force what you applied must be equal to the mass into acceleration. This is only applied for the particles which are in considerable size. But coming to the particles which are smaller size, when you are decreasing the size of the particle size, we undergo the smallest particles which we consider as the electrons in atoms. But it is not preferable and it is not easy to mix the Newton's law with the quantum particles. So a new branch of physics has developed. It is called quantum physics, which comes the minute particles and their properties. And these properties was explained by the great scientist called Schrodinger. The equation which he proposed is will explain the properties of minute particles. As we know that the properties of the electrons may behave as the particle nature and wave nature. The particle nature and wave nature was excellently explained by the Schrodinger equation.
As we know, this is the Schrodinger equation on the origin, which is a cornerstone of quantum physics. Quantum physics describes the system of quantum objects such as atoms and subatomic particles will do in the future based on its current state. Although the Schrodinger equation was published in 1926, the authors of a new study explain that the equation's origins are still not fully appreciated by many physicists. And the classical analogies are Newton's second law and Hamilton mechanics.
So that ends the needs of Schrodinger's equations from S.R. Sanjay Kumar, the member of NANTICOS.
Hello everyone, I'm Abhilash. I'm going to talk about Schrodinger's wave equation. Why do we need Schrodinger's wave equation? First of all, let me give a small introduction about Schrodinger's wave equation. In the 20th century, scientists found that atomic particles have wave-like properties. For example, they made electrons pass through the double slit, and the result was they showed diffraction patterns were similar to the light waves. So it was reasonable to assume that the wave equation will explain the behavior of atomic particles. And it was during this time Schrodinger introduced the wave equation. So let us see, why do we need this Schrodinger's wave equation? Eigenvalues of the wave equation where it's shown to be equal to the energy levels of the quantum mechanical system. It was used to solve the energy levels of hydrogen atoms. Schrodinger wave equation is used to find allowed energy levels of quantum mechanical system. Wave function gives the probability of finding electrons at a certain position. Schrodinger equation shows all the wave-like properties of matter. It is used in physics and in some parts of chemistry to deal with the problems about atomic structure.
Today we will learn about Schrodinger's wave equation. Schrodinger's wave equation is basically classified into two parts, that is Schrodinger's time independent equation and Schrodinger's time dependent equation. Wave function of any particle that is traveling in the nanoscale is a function of or is dependent on two variables, that is position of the particle and time, denoted by psi x of t equal to amplitude of the wave denoted by a into exponential of iota omega t minus kx. From this formula, we can see omega is written as 2 pi into nu, where nu denotes the frequency. Equating this formula in this equation, and value of k is given by omega by v. Expressing these two equations, in this equation number 1, we get amplitude a into e to the power iota 2 pi nu t minus, instead of k we write omega by v, omega x by v, and v equal to lambda into nu. We know this as equation 3. Substituting this in equation 2 and taking 2 pi common outside, we get psi x of t equal to a e to the power iota 2 pi nu t minus x by lambda. Then multiplying this equation, here multiplying by and dividing by h, we get here, as we see in this equation, multiply this outside term by the inside term and multiply divided by h. Here h stands for the Planck's constant. As we know that h cross is equal to h by 2 pi. Hence, we can take this 2 pi below and we can form a new equation which says iota by h cross into h nu t minus iota 2 pi x by lambda. Of the exponential part, we can multiply and divide by h. Hence, psi x of t equal to a e to the power iota 2 pi by h into h nu t minus x h by lambda. As we know that psi x of t equal to a e to the power iota. Bringing this 2 pi down, we get h cross. H nu will be equated with e t minus, by, as we know by de Broglie's equation, lambda equal to h by k, and hence h by lambda will be equal to p. Hence this is the final equation. Now my friend Sayus will tell you the further steps of this Schrodinger's equation.
With the equation which Mayuresh derived, psi x of x cross t is equal to a e to power I by h cross e t minus t. Extending this, we get now d by dx of e to power x is dx, but in this a constant is there besides x, so it will come outside. So it will be I h into minus p. So minus I p by h cross exponential of I by h cross e t minus p. There is this equation with respect to x, we get d square psi x of t by d x square. Now again when we differentiate this d by dx of this function, again this I by H cross into P will come. So it will be A into minus IP by H cross into minus IP by H cross exponential of I by H cross P of T into T minus Px. So it will be A. Now I into I square, it is minus 1 and this will get cancelled. So minus I will come outside, it will be minus A P square by H cross square into e की power I by H cross T minus Px. So as we double differentiated the wave function psi with respect to x, we got this equation. Let it be some x. Now what is psi? Psi of x of t is a e की power I by h cross e t minus px. So replacing this value as psi here, we will get minus p square by h cross square, and this will be psi. When we differentiate this wave function with respect to t, we will get d psi x of t by dt equal to, now same as earlier, differentiation of e की power t, this e की power t, the remaining part constant will come outside, it will be I e by h cross. I e by h cross into a e की power I by h cross dt minus px. Now again e की power I by h cross dt minus px is equal to psi x of t. So replacing it, we get I e by h cross into psi. This is another equation by. Now when we differentiated the wave function with respect to t, we got I e by h cross into phi. Now cross multiplying it, we will get h cross d psi by dt is equal to I e into psi. D psi by dt was minus I by h cross e psi. So when we cross multiply this, we got h cross d psi by dt is equal to minus I e phi. So now multiplying both the sides by I, we get I h cross d psi by dt is equal to minus I square will become plus 1. That will be equal to e psi. That will be one equation. Now as we already found out, d square psi by dx square is equal to minus p square by h cross square psi. Cross multiplying this side, we get h cross square d square psi by dx square is equal to minus p square psi. Now assume that there is a nanoparticle which is traveling with the speed of light, same as like that of electron. Now if we apply the principle of energy conservation, then total energy is equal to potential energy plus kinetic energy. So this is potential energy at position x comma y plus kinetic energy. So total energy, let it be E. Now U is U of x and y, this is potential energy. Now what is kinetic energy? It is half mv square, as you all know. So this is half mv square, which can also be written as p square by 2m, as momentum is equal to mv. So if we substitute the value of p, it becomes p square by 2m. This is one equation. We got this equation, E is equal to U of x of y plus v square by 2m. Multiplying both the sides by the wave function psi, we get E psi is equal to u psi plus p square psi by, as we multiply wave function psi both the sides, we got this equation. Now substituting the value of E psi and p square psi from equation 1 and 2. So E psi will be IH d psi by dt. IH cross d psi by dt is equal to u psi plus, now p square psi is equal to minus h cross d square psi by dx square. So minus h square by 2m d square psi by dx square. So the final equation will be IH cross d psi by dt is equal to u psi minus h cross square by 2m d square psi by dx square. This is the required Schrodinger equation in time dependent form.
Good morning friends. Today, me Amit Kumar is going to tell you about the time-independent Schrodinger wave equation. Well, before my friends Mayuresh and Siraj have already told you about the Schrodinger time-dependent equation. And today, I'm going to derive the same equation, but it will be time-independent equation. First, let's see what is the time-dependent equation. It is dou square by dou x square plus dou square by dou y square plus dou square sine by dou z square is equal to minus 4 pi square by h into 2m e minus v sine. After this equation, we are going to see one more new thing, that is the Laplacian operator. The Laplacian operator is denoted by del square, and it is del square is equal to Laplacian operator which is equal to dou square by dou x square plus dou square plus dou y square plus dou square by dou z square. Hence, our equation now becomes del square sine is equal to minus 8 pi square by x square into m e minus v sine. Now by rearranging the terms, we get dou square sine plus 8 pi square by x square into m into e minus v sine. Now we also know that h cross is equal to h by 2 pi. And now if we substitute this in our equation, we get del square sine plus 2n h cross square into e minus v sine. Now in order to get the time independent equation, we have to eliminate e. In order to eliminate e, we are going into a new procedure. In order to eliminate e, we are going to proceed to a new procedure, that is dou psi by dou t is equal to minus I omega naught into psi into e to power I omega t. We already know that omega naught is equal to 2 pi nu. Hence, we are going to substitute omega naught into our equation. So now it becomes minus I into 2 pi nu into phi into e to power I omega t. Now since it is a time independent equation, we have to substitute 0 into our time. So let t is equal to 0. Hence our equation becomes I into 2 pi nu into psi into 1. Now we also know that E is equal to h mu. Hence we can substitute E is equal to h mu. Hence, our equation now becomes I into 2 pi mu 2 pi into E by H into psi. We also seen that H cross is equal to H by 2 pi. Our equation is, now our equation becomes minus I into E by H cross into psi. In the terms, we get E psi is equal to dou psi by dou t into H cross into minus 1 by I. Now, to eliminate I, we'll do complement to dependent, and that will come to E psi is equal to I in I H cross dou psi by dou t. Now we substitute this value into our equation. Now our equation becomes del square psi plus 2m H cross into, instead of E we use I H cross into dou psi by dou t minus V psi. Now we multiply both sides by H cross by 2m minus H cross by 2m. We get the equation minus H cross by 2m into del square psi minus H square H cross psi into dou psi by dou t minus V psi equal to 0. Now by rearranging the terms, we get H cross 2m del square psi plus V psi, which is equal to I H cross V psi by dt. Hence, now we are going to use a new operator, that is, we are going to take this common and this will become H, which is also known as Hamiltonian operator. And this we are going to take as E, which is the energy operator. Hence, by rearranging the terms, we get H psi, which is equal to E psi. Hence, our final energy equation has become H psi, which is equal to E psi, and the equation was H square by 2m del square plus V into psi, which was equal to I H cross dou psi by dt. This is our final time-independent Schrodinger equation.
Measurement in an uncertainty, Schrodinger's equation has some really important results. In classical mechanics, a particle has at every moment an exact position and an exact momentum. These values change deterministically as the particle moves according to Newton's law. Under the Copenhagen interpretation of quantum mechanics, particles do not have exactly determined properties, and when they are measured, the result is randomly drawn from a probability distribution. The Schrodinger's equation predicts what the probability distributions are, but fundamentally cannot predict the exact result of each
There are
measurement.
several applications for Schrodinger equation, and one of them is quantization. The Schrodinger equation predicts that if certain properties of a system are measured, the result may be quantized, meaning that only specific discrete values can occur. One example is energy quantization. The energy of an electron in an atom is always one of the quantized energy levels, a fact discovered via atomic spectroscopy. Another example is quantization of angular momentum. This was an assumption in the earlier Bohr model of the atom, but it is a prediction of the Schrodinger equation. Another result of the Schrodinger equation is that not every measurement gives a quantized result in quantum mechanics. For example, position, momentum, time, and energy can have any value across a continuous range. Another very famous application is the quantum tunneling. In classical physics, when a ball is rolled slowly up a large hill, it will come to a stop and roll back because it doesn't have enough energy to get over the top of the hill to the other side. However, the Schrodinger equation predicts that there is a small probability that the ball will get to the other side of the hill, even if it has too little energy to reach the top. This is called quantum tunneling. It is related to the distribution of energy. Although the ball's assumed position seems to be on one side of the hill, there is a change. There is a chance of finding it on the other side.
Now, Schrodinger equation also talks about particle as a wave. In quantum mechanics, the Schrodinger's equation is a partial differential equation that describes how the quantum state of a quantum system changes with time. It was formulated in late 1925 and published in 1926 by the Australian physicist Erwin Schrödinger. In classical mechanics, Newton's second law, F is equal to ma, is used to make a mathematical prediction as to what path a given system will take following a set of known initial conditions. In quantum mechanics, the analog of Newton's law is Schrodinger's equation for quantum system, usually for atoms, molecules, subatomic particles, whether free, bound, or localized.
So before we get into the Schrodinger's cat experiment, we need to know why he has thought about such a kind of cat experiment. It's because to show the flaws of Copenhagen interpretation of quantum superposition. According to it, a particle in a physical system can exist in all the simultaneous possible configurations till the time when no observation has been taken place. When the observation has been taken place, then we will come to know about the reality and the simultaneity collapses.
So here we are to talk about the Schrodinger's cat. Now what happened exactly was Erwin Schrödinger proposed a thought experiment where he took a cat and placed it inside a cartoon. This way. And with that he also put a radioactive material which had a 50% chance of killing the cat. Now after an hour, common sense would suggest that the cat is either alive or dead. But according to quantum mechanics, Schrödinger proposed that the cat is 50% alive and 50% dead at the same time, the moment before we open the box. Now after that, when we open the box, we come to a definite conclusion. Now this was philosophically disturbing, and instead he turned into biology.
Yeah, and instead he did not turn into
So we saw Saurav explaining the Schrodinger's cat thought experiment. Well, this thought experiment gave rise to an entirely new phenomena called superposition. Superposition says that matter can exist in all its possible forms before it is observed. Well, superposition is a result of the dual nature of matter, which says that matter can exhibit both particulate as well as wave characteristics simultaneously. Well, during propagation, matter exhibits wave characteristics, as you can see in the case of diffraction, and it exhibits particulate characteristics during interaction, as we see in the case of reflection and refraction.
So concluding, in quantum mechanics, results of Schrodinger equation can be used to get allowed energy levels of a quantum mechanical system such as atoms, transistors, and also finding probability of finding a particle at certain place, and many more such things. So hope you all like the video. Editing is done by me. Thank you for watching.